This short presentation is about turbulence and phytoplankton. I'm François Schmidt, Research Director at CNRS, and it is also done in the framework of the graduate school IFSI about marine fisheries and seafood sciences. So there are some few words about the context about turbulence and marine ecosystems. So turbulence plays a big role in marine ecosystems through mixing, transport of particle, transport of different quantities, and also the contact rate between particles. So there had been some words saying that, in fact, turbulence is necessary in nature in order to have life. And Margalef, so in 1997, summarized this by saying that there is no life without water and there is no life in water without turbulence. About plankton, so plankton lives in suspension in water. It is fully adapted to the turbulent environment because there have been a lot of generation during a million years. It's subject to Lagrangian transport, and if we consider phytoplankton, so its turbulence will be important through the diffusion of nutrients and also considering the transport, and especially along the vertical. Because as you know, there is a photosynthesis close to the surface of the water, and the question of the transport of particles close to the surface is important in this context. Also, in fact, by looking at different pictures of different species of phytoplankton, we can see that they have many different shapes. Also, some of them are able to swim, so they have motility. And globally, they have adapted their shape to different turbulent conditions. So in fact, the word plankton comes from the Greek, meaning passive wandering. And this is in fact not so valid anymore because we know that plankton is able to adapt through different strategies to the turbulent transport. So if we consider also diatoms, diatoms have many, so 200,000 different species. They have many different shapes. They have isolated cells. They have also chains. They're not motile, and the effect of turbulence for them is mainly through the diffusive fluxes. So a word also about the scales. So the scale of turbulence, the small scale of turbulence for the velocity is a Kolmogorov scale. And for the nutrients, it is a Bachelor scale. And we can see here that more or less phytoplankton has a scale which is between the Bachelor and Kolmogorov scale, meaning that turbulence can have some influence on the phytoplankton. So one of the first results that have been proposed in the field of relation between turbulence and plankton is coming from Margalef. It's so-called Margalef mandala. The origin of it is a proposal, a model proposed by Vito Volterra 100 years ago. And in one of these models, in fact, if we consider two species using the same resource, only one can maintain over a long time. So a bit later, this was called the struggle for life. And also it was used in the 60s by Hutchinson to propose what is the so-called plankton paradox, asking how can we have so many species of phytoplankton in the same region, sharing the same resource? What he called, in fact, the same ecological niche. And one possible answer is in the fact that the field is not so homogeneous. They are different in nutrients, in turbulence, and also in different physical variables. And so that each species should be adapted to a given environment. So Margalef proposed in this context to study the influence of turbulence and of nutrients. And he proposed in this paper and also in other papers in the 70s to consider dinoflagellates and diatoms. So dinoflagellates are motile. They can seed food, but for this they need energy. Diatoms have no swimming activities, and they need turbulence to find the nutrients, and especially when there is not so much nutrients in the field. So the relation which was proposed by Margalef is a kind of diagram where you consider nutrients abundance on the vertical and turbulence intensity in the horizontal, and you can see that dinoflagellate and diatoms occupy different places in this diagram. So his prediction said that in water with weak turbulence, we will find more dinoflagellate, and in region of strong turbulence, we will find more diatoms because they have an advantage. Since the 80s, there have been many experimental works. I show here results from a few of them. So in this work, which is cited here, we can see there was a culture of two species, one species of diatom, one species of dinoflagellate. Turbulence was generated using a moving grid in a framework of poor nutrient concentration, and the result showed that turbulence had more effect on the diatom culture than on the dinoflagellate culture. Another work considered another species. It's a freshwater species, and here we can see that the turbulence is generated by a system using some speakers. And turbulence, there were several levels of turbulence which are quantified in a table shown here, where you can see the dissipation, epsilon, Kolmogorov scale, Bachelor scale. So by changing the frequency of the speaker, different turbulence intensity were generated. And the results showed that a larger growth rate was formed for stronger turbulence. And if we consider, for example, here, day 3, abundance of phytoplankton, we can see that there is an optimal turbulence intensity for a median value of turbulence. So globally, I don't show here all the works, of course, that exist using continuing experiments of phytoplankton in turbulence. So we have many studies in the 80s on the impact of turbulence on phytoplankton. Most studies did not consider many turbulence level, but still Margalef mandala was mainly verified. And it seems also that there is an optimal level of turbulence for phytoplankton growth. So too much turbulence will destroy the chain, for example, and it will also limit the growth. So we can also consider numerical simulation of particles in turbulence with application to phytoplankton. So since the years 2000, particle dynamics in turbulence can be numerically studied. So in this case, velocity turbulence is simulated in 3D by a direct numerical simulation of the Navier-Stokes equation, and of the order of 100,000 particles, so it's a large number, are distributed in the system, and at each time step, the Lagrangian dynamics is numerically solved. So the question is to know what is the equation for the particles. And so the answer is the fact that it depends on their shape, their density, and their size. The equation was given in 2 papers in 1983. You can see that it's a complex equation. We have different parameters. So we have v is the velocity of the particle, u is the velocity of the fluid, which is given by the DNS. We have the density of the particle, the density of the fluid, the diameter of the particle, and beta is a parameter, and 2p is the reaction time of the particle. The different terms correspond to the drag of the particle, to the gravity term, and also an history term. So it's a complex equation, but it's too heavy, in fact, to simulate all these terms, but they can be simplified in some cases. For example, when the particle is of small size, the equation is simplified. You can see also that for heavy and small particles, it's even simpler. And for phytoplankton, so when we assume that the particle density is close to the density of the fluid, we have the last equation which is given here. So it can be solved. And in fact, this corresponds to spherical particles. And of course, we have seen that the phytoplankton cells have many different shapes. So it can be approximated by what is called elongated spheroids. You can see here two examples. One is like a rugby balloon, so it's called a prolate particle. The other one is like more or less a cake, and so it corresponds to a oblate, what is called oblate particle. And in this case, in fact, there is a new equation which can be used. In fact, it's an old equation which was proposed 100 years ago, which is shown here. I don't explain all the terms, but more or less it's an equation that can be solved by considering the shape of the spheroid, and also by considering the orientation vector of the particle. Because you can see here we have an illustration with a copepod or with a small spheroid. We can see, in fact, that the orientation of the particle is not necessarily in the same direction as the velocity of the particle. So in fact, this equation, which is called Jeffrey equation, is taking this into account. So I don't list here all the results of the different works that have been done, but globally we can say that for these studies, the dynamics is solved by doing the DNS of Navier-Stokes equation in the Eulerian way. Particles are solved using a Lagrangian expression for particle dynamics. The shape is taken into account by a Jeffrey equation for the orientation. In some studies, I did not mention it, but we can find several papers published in this case. So in some cases, the motility can be numerically modeled, and it can work mainly for species that swim against gravity. So the result of all these species, of all these studies, is the fact that the effect of the shape can change the sedimentation of phytoplankton cells, and also that motility can lead to clustering of the particles, and so it's called patches of particles. So there have been many numerical studies of this type in the last 10 years, but still there is a lot to do because there are hundreds of species that exist with different strategy, different shape, etc. So it's only the beginning of a new field that we have here. And the connection between numerics and ecology is only beginning in this kind of work. So that's all for this short presentation. Thank you.